Welcome teachers to this course on NMR spectroscopy and its applications, which is a part of a module called ChemSimplified. In this particular lecture, I am going to tell you about the general principles of NMR spectroscopy and its applications, which will be essential for you to know. So let us start to look at the major pioneers who have contributed to this technique development, and technique has evolved over the period of last 6 decades or so, or 7 decades rather. So 1945 was the first discovery in the condensed phase, but actually it started even before that. To tell you about these ones, so initially it was a technique which originated in the realm of physics, and then here there were 4 Nobel Prize winners for this. Otto Stern in 1943 got the Nobel Prize, and this was followed by I. Rabi in the very next year 1944, and these were Nobel Prizes in physics, and this was followed by Felix Bloch and E. Purcell in 1952. These were independent researchers at 2 corners of America. One was in Stanford, other one is in MIT, and then this was followed by applications in chemistry which also won Nobel Prizes, and this was Richard Ernst in 1991 and Kurt Wittrich in 2002. Both were at ETH Zurich, where they conducted their research. And then look at this, it also entered the realm of physiology and medicine, and this also led to 2 Nobel Prizes, well, 1 Nobel Prize shared by 2 people, Peter Mansfield and Paul Lauterbur. And it is amazing to see what kind of a background these people had. They originated in the field of electrical engineering, and then they actually contributed to the development in such a way that they won the Nobel Prize in physiology and medicine. All of you have heard about MRI, which is a common technique in all hospitals, magnetic resonance imaging, but that is nothing but NMR, nuclear magnetic resonance. And so therefore all these have contributed immensely to our lifestyle today, in our day-to-day working and day-to-day life, and therefore it is important for us to know the general principles of this technique, which has revolutionized our lives. As we are talking about NMR spectroscopy, it is, as I said, it has gone through many revolutionary developments, and I am to list here some of those which have made such an important role in the development of NMR spectroscopy per se. As you will see, the very first experiment which actually caused this revolution was in 1922 by Stern Gerlach. They actually discovered the nuclear magnetic moment, and this was followed by an application of this by Rabi, and this was a molecular beam experiments where he actually discovered magnetic resonance in the molecular beam experiments, and that was an important discovery. And then it was followed by another discovery in the condensed matter phase, and that was in 1946, basic discovery by in the condensed matter phase. This was again done by 2 physicists. All along this have been in the areas of physics, and in the period 1950 to 55 a number of discoveries were made: chemical shift, coupling constants, Overhauser effect. All of this you can see, spin echo, and spin echo is also such an important development. This actually almost would have fetched a Nobel Prize, but somehow it missed it, but never mind. That is an important technique which has played a very major role in all modern developments in NMR spectroscopy. In the 1960s we have these discoveries of spin decoupling, cross polarization, and then in 1966 a major revolution came up, as you can see there, Fourier transform NMR. This was done by Richard Ernst while working in a company in Varian which worked with radars, and this was then followed by an important development called 2-dimensional NMR in the 1970s. 71 to 76 was a boom period for the development of 2-dimensional NMR, and parallelly there was another application which was coming up, that was called NMR imaging. How you can use NMR to image objects, and this has now become a common tool in all hospitals. MRI is a technique which is used in the hospitals to diagnose various kinds of diseases, and we have this indispensable tool in all hospitals. And then in the 1980s, multidimensional NMR came up, and this was actually an extension of two-dimensional NMR, and this again caused a revolution and entered in the realm of biology, chemistry, and other related subjects. So protein structure determination, all that became possible because of multidimensional NMR, and this also won the Nobel Prizes as are listed here. You can see here the 1943 Nobel Prize was in physics, 1944 Nobel Prize was in physics, and 1952 there was Nobel Prize in physics for two persons, Felix Bloch and E.M. Purcell, and 91 Nobel Prize was in chemistry to Richard Ernst, and 2002 Nobel Prize in chemistry for Kurt Wittrich again, and then in 2003 there is a Nobel Prize in physiology and medicine for Paul Lauterbur and Peter Mansfield. Therefore you can see that NMR spectroscopy has entered in all branches of science, ranging from physics into physiology and medicine. The people who have contributed have come from different disciplines. There were theoretical physicists, there were physical chemists, there were electrical engineers, and all of these have made this technique such an indispensable tool that you cannot live without it today. So therefore it is very important for all the teachers to know about what it is and to see how you can use it, and teach the students, of course, who will be the future research scientists for the modern world. In order to understand the basic principles, let us look here. What does it contain? You can see here there is a magnet and there is a sample in between, and that sample consists of your molecules which are of interest, which your specimen of interest you want to study. So these molecules or the samples what we will have, these consist of nuclear magnets, tiny magnets, and these have certain energy in the magnetic field. So and that you can see that if I take typically the nuclear magnets of protons, carbons, nitrogen 15s, these are the ones which we normally observe in the case of NMR spectroscopy in chemistry. And in the absence of the magnetic field, these nuclear magnetic moments can orient themselves with respect to the magnetic field in any direction, but however when you have the magnetic field, they have two particular orientations which are represented by two spheres over there, and there is an energy difference between them, and that depends on the strength of the magnetic field. Now at any particular magnetic field there is a certain energy difference between the two orientations of these magnetic moments, and then if you supply energy corresponding to that energy difference, there will be absorption of energy, and that is your NMR signal. Now what is the intensity of the NMR signal? How much energy will be absorbed? So this is an important question. That is the strength of the signal. Now when you have two energy levels, the nuclear spins will distribute themselves between these two energy levels according to a certain law which is called the Maxwell-Boltzmann statistics, and then the intensity will be proportional to the population difference between these two energy levels. So therefore that is the NMR signal what you will get in your NMR spectrometer. Now let us look at some of the very basic discoveries in this context. One thing is the chemical shift. The first thing which I already mentioned to you, this is the chemical shift. What is this? Every nucleus, you can see, which is the red circle in the middle, you can see that in the center, every nucleus is surrounded by an electron cloud which is represented here by green spots, and when you apply magnetic field which is represented by B naught, it actually induces current in this electronic cloud, because of which additional magnetic field is generated. This will tend to oppose the externally applied magnetic field as indicated by the tiny arrow near the nucleus. Okay? Therefore the effective field what the nucleus sees is reduced compared to B naught, and if I represent this as Bi, it is given by B naught into 1 minus sigma I. Sigma I is called the screening constant, and this actually tells you what is the electronic cloud around the particular nucleus. This is of importance because different nuclei will have different environments in a given molecule, and therefore they will absorb energy at different frequencies. Now, if I supply energy corresponding to separation between the two energy levels, as I mentioned before, then there will be resonance absorption of energy, and that is given by a nu I. That is the frequency of absorption, which is proportional to minus gamma bi divided by 2 pi. Sigma I is called the screening constant, and this reflects upon the environment the particular nucleus is around. Now, to make this a number which is independent of the externally applied magnetic field, you define a particular term called delta I, which is defined as nu I minus nu r divided by nu naught. And therefore, now this the field dependence will go away, and whatever delta I you get is clearly representing the environment a particular nucleus is, electronic environment, and therefore we call this as a characteristic of particular nucleus. Chemists use this quite extensively to understand molecular structures. For example, I have here a molecule which has vinyl chloride, which has 3 protons in it. The 3 protons are A, B and C, and in this vinyl chloride these 3 protons have different chemical environments. Why? Because the chlorine group is electron withdrawing, and if it withdraws the electrons, the density of electrons around the 3 different protons A, B and C are going to be different. So wherever the electron density is very, very low, the field seen will be the highest, and therefore that will absorb energy at the highest frequency. So in this particular case, you see the B proton absorbs energy at the highest frequency, and this will be followed by A and followed by C. Therefore, in this molecule there will be 3 resonance frequencies which are called as nu A, nu B and nu C. So chemists use this quite extensively. Now, depending upon what group you have in your molecule, earlier I showed you the chlorine group, but there may be various other groups. You can have the OH groups or the NH group or the aromatic groups, various kinds of groups you might have, and then they will absorb energy at different frequencies. Accordingly, you convert them into that particular delta number. The delta number is now represented as a ppm, parts per million, because you remember there was nu I minus nu r divided by nu naught. So this is actually in ppm, because nu naught is in megahertz and nu I minus nu r is in small kilohertz range, and therefore this can be a parts per million. Typically in a proton, these ppms go from 0 to 12 ppm. This is called as different chemical shifts, and these numbers are very characteristic of the molecular structure and what is present as a substituent in your molecule. So in this you can see there the various substituents which are there in the molecule produce peaks at different chemical shifts, and this is a very characteristic feature which will allow a chemist to understand what molecule he has and what he has synthesized has these particular groups or not. This was for the protons. You can do the same thing for carbons. The carbons also have, you can see, a wide range of chemical shifts, a whole range of chemical shifts. It goes from 0 ppm to 220 ppm, much wider range compared to the proton. Therefore, this is extremely useful for organic chemists to see what sort of a structure your molecule might have, whether it is a carbon-carbon single bond, whether it is attached to a double bond, attached to a triple bond, or there is a carboxyl group there, or an aldehyde group there, or a methoxy group there, aromatic group there. Depending upon what all kinds of groups you might have, you will have different kinds of chemical shifts. It goes from 0 ppm to 200 ppm. So normally, if you have aliphatic groups, you will have chemical shifts of carbons around the 10, 20, 30 ppm. The moment you go to carbonyl groups, the carboxyl groups and things like that, you go to 200 ppm, and the aromatic groups, they appear around 100 to 120, 130 ppm. Therefore, looking at the signals where you get these, you can actually identify what sort of a molecular structure you have in your study. So the next important parameter, the discovery which was made in NMR, is called as spin-spin coupling. So earlier we talked about the interaction between the proton and the externally applied magnetic field, which resulted in a shielding or a de-shielding and led to the chemical shift. Now here you have two consider this molecule CHCl2CHO. There are two protons here. Now each proton is a tiny magnet. Therefore the proton itself can influence the other proton, and that can cause a change in the magnetic field around the particular nucleus, and therefore it can result in a different energy of absorption. So in this particular case, now if you look at one particular, the red proton for example, and it will depend upon what the frequency of its absorption will depend upon what is the blue proton doing. If the blue proton is oriented parallel to the magnetic field, the red one will absorb at a particular frequency. If the blue one is oriented opposite to the magnetic field, then it will absorb energy at a different frequency. So therefore you will have two kinds of absorption energies, and this we call as splitting. This is due to the spin-spin coupling. Typically this is mediated through the electrons in the intervening bonds. Just as the red proton will be split into two, the blue proton also will be split into two, so you will get two doublets for this particular molecule. In the proton spectrum we will have two doublets for the individual protons. So this is illustrated here in an experimental example. You take this ethanol. Ethanol molecule is CH3CH2OH, and there are three kinds of protons here. The OH group you can see there, and then you have the CH2 group, then you have the CH3 group, okay, and all of these are labeled here. The CH3 group has 3 protons, therefore the total intensity of that signal will be much more than that of the CH2, which has 2 protons, and the OH group is 1 proton. The integrated intensity of these groups is going to be accordingly different, and then they will absorb energy at 3 different frequencies, and these are in the ppms. If you see, the CH3 protons absorb energy at 1 ppm, and the CH2s appear at about 3.5 ppm, and the OH protons appear at about nearly 4.7 4.8 ppm. And then you can also see that there is a fine structure in each one of those. The CH3 group of protons are coupled to the neighboring CH2 groups, and these, because there are 2 protons there, the CH3 protons are split into 3 lines with the intensity ratio 1:2:1, and likewise the CH2 protons which are adjacent to the CH3 protons will be split into 4 lines with the intensity ratio 1:3:3:1, and the OH proton will be coupled to the CH2 proton, and that will also be split into 3, but however the separation is too small, and therefore you see a triplet, but the other intensities are slightly appear smaller than the other. But this is to illustrate how the chemical shifts and the coupling constants tell you about the molecular structure you have in your system. Now how do we measure this? How do we measure these frequencies absorption? And this is an important point. In the early days, what one used to do was keep the frequency constant and sweep the magnetic field. When you sweep the magnetic field, the populations will change between the energy levels. They have to adjust themselves to the new field, and therefore this is a slow process. This is called as relaxation, and the relaxation process is slow, and because it has to interact with the surroundings, and that is a slow process. So typically if you have a relaxation rate of 1 second or something, then you will have to give reasonably slow sweep through the spectrum, and if you sweep at the rate of 1 hertz per second, suppose I have a 1000 hertz spectrum, a total of 10 ppm assuming for a 100 megahertz NMR spectrometer, then this will be 1000 hertz for a 100 megahertz NMR spectrometer if it is 10 ppm. Now if I sweep at the rate of 1 hertz per second, this will take me 16 minutes. 16 minutes is a long time. If you want to improve the signal to noise ratio of in your spectrum, the signal to noise ratio is defined in the particular manner as indicated here. So if you have the noise, then you have a signal, and then you take the measurement of the height of the signal above the noise level, and you also take the noise maximum peak to peak separation in the noise, it will take the ratio and multiply by 2.5, and that gives you the signal to noise ratio. Now generally in NMR the signal to noise ratio is rather small, because at the radio frequency level the population differences are small, and therefore the energy absorbed will be small. Now if you want to improve the signal to noise ratio, what you will have to do? You have to do what is called as signal averaging, and you can see there signal averaging means you collect a number of sweeps and add them, and then when you do so your signal to noise goes as the square root of the number of sweeps you added. For example, if I want to get a signal to noise enhancement by a factor of 10, I will have to add 100 sweeps. So that means it will take me 1600 minutes, and that is a huge amount of time. Magnetic field was generated by electromagnets, and then that will generate a lot of heat, and you will have to have a power which is stable. Therefore this is a very demanding thing to have a spectrometer which is stable for so long without any disturbances, and that was a problem. And therefore this issues of stability of the spectrometer, the stability of the samples has also is a concern. And then when you could not have that, then you have to have high concentrations. High concentrations means you have to have several hundreds of millimolars of samples will be required, but then the solubility will be a problem at that point, and therefore it was difficult to observe low abundance nuclei such as carbon 13 and nitrogen 15. Now remember, carbon 13 is only 1.1% in natural abundance. Nitrogen 15 is 0.37% in natural abundance. And why do we need carbon 13, nitrogen 15? Because carbon 12, which is the most abundant one, doesn't have a magnetic moment, and that doesn't give an NMR signal. Nitrogen 14, once again it is 100%, but there is a quadrupolar nucleus, it has its own problems, and therefore that is not a suitable nucleus. So typically carbon 13 and nitrogen 15 are the two nuclei one would like to observe. However, this was difficult in the case of slow passage experiments. Okay, and therefore you required some changes, and the pulse excitation became a tool. This was created, the one which was exploited. This was exploited by Richard Ernst, as I will show you. What is pulse excitation? Now in the normal experiment, you have the radio frequency, the wave which is going as a function of time. You can see the RF is a continuous wave which is going like this, and then if you don't do anything, it will keep going like that. However, if you apply this for a short time, as indicated there, for a short time tau, you start, apply for a short time tau and stop, and that is a pulse, that is an RF pulse. So what is the consequence of that? The consequence of that will be so many different frequencies will be excited. As you can see there, you have a plot of the amplitude versus the frequency of the ones which are generated. So this is called as a sync function, and you will see a large number of frequencies are generated with the different amplitudes. Omega naught is the frequency you applied, and then it generates various other frequencies around it, and you can see its amplitudes are different, and it has a distribution, and the distribution comes down to, it becomes 0 at 1 by tau. Tau is the time for which you apply the RF. Now imagine that your tau is 1 microsecond. If it is 1 microsecond, then 1 by tau is 10 to the power 6, so that is a megahertz. So megahertz of frequency range is covered on each side of your omega naught. So a huge frequency range is covered, whereas you don't need that much, really speaking, but you also need all of them with a similar amplitude. Therefore, as you can see there, I indicated a shaded area, which will tell you which is the region which is of interest for us. Around omega naught, we choose a few kilohertz, and those few kilohertz are the ones which have the similar amplitude. They have similar amplitude, and therefore they will excite your spin system to the similar level, because the excitation efficiency is dependent on the amplitude of your RF, because that is, the power is proportional to the square of the amplitude, and the power determines how much is the energy absorbed, and therefore you need to have similar amplitude. And therefore what you do a thing called filtering. So you filter out the other frequencies, you choose only those which are required for you in the central portion. So this is what was indicated to you in a particular manner, and now we look at the spins in a magnetic field in a slightly different approach, a sort of a classical approach. And you see, suppose you have an ensemble of spins, let us say there are 1 trillion spins in your sample, and all of these nuclear tiny magnets, all of these called spins, the tiny magnets, they distribute between the 2 levels, but each one of those has the 2 orientations. They will spin around the axis of the magnetic field in a particular fashion, and this is called as Larmor precession. And all of these spins will distribute themselves at different places on the surface of the cone. The ones which are on the top, they will all be going like this, the which are in the bottom, they will all be going like this, and therefore you will have the complete cone covered by these nuclear spins. And in terms of the energy levels, the ones which are parallel to the magnetic field have a lower energy, the ones which are anti-parallel to the magnetic field have a higher energy, and then when you supply energy the radio frequency corresponding to this energy separation, you will have the absorption of energy. And this mathematically, this is given by the interaction between the magnetic field and the magnetic moment is described by minus mu dot h naught, and that is given by mu z h naught, where mu z is the component of the magnetic moment on the direction of the field. Now let us look at this in a particular way. Suppose I apply an RF and the radio frequency is applied along the transverse plane. So it is applied, as you see, you have the spins going around like this, and then I have the RF which is applied, which is in a particular component of that is in the transverse plane, which is going like this. Now, and the amplitude of this RF is represented by H1, and the amplitude of your main field is H naught. Now suppose you sit on the RF and look at the spins which are precessing in this plane. So what will happen? They will see a different frequency of precession, right? So if I call that as omega IR, omega I is the frequency of precession in the normal frame, and omega naught is the frequency of our RF. Then if I sit on the RF and look at the nuclei which are precessing, then what do I see? I see that they are precessing with the frequency omega I minus omega naught. Now this omega I or omega naught, this precessional frequency, I want to convert it into a magnetic field, and that I call it as HIR. HIR is equal to omega I minus omega naught divided by gamma. So that is, gamma is a constant which is characteristic of a particular nucleus, and the precessional frequency is given by gamma times H naught, okay, and for the main frequency, or gamma times Hi, or and then it will give you omega I. So Hi, if I now write that in the along the z axis, in the rotating, this is called as a rotating frame. If I sit on the RF, means I go into the frame of reference, which is called as a rotating frame. If in that rotating frame of reference, then your field along the z axis is given by HIR. So therefore I represent that as a vector along the z axis, which is HIR, and then in that frame of reference the amplitude which is the of the RF is H1. So then what happens? Now I have to calculate an effective field of these two fields we have. I have the HIR and the H1. So therefore there is an effective field of this which is calculated as a vector addition of this, and that is represented as H effective. This H effective will have a different orientation with respect to the main field, right? So that is a vector addition. I add HIR and H1, I get a vector addition which is a effective field indicated by the cyan arrow, and now your nuclear spins which are initially going around the H0 field will now go around the H effective field, because they will rotate around the H effective field, right, because they have to orient themselves. So therefore they will tilt away from the z axis and go around the H effective. So this is indicated by these equations here, and now if I have HIR effective is given by this particular equation, and you have omega I minus omega naught whole square plus gamma H1 whole square. You take the square root of that divided by gamma, and this is your HIR effective. Now assume that the H1 field which you apply is so large that it is much larger than omega I minus omega naught. Okay. So whatever the value of omega I is, regardless of that, I suppose I make it so large that omega I minus omega naught is much smaller compared to the gamma H1, then what happens in the top equation? The top equation, I can ignore the omega I minus omega naught dependent term, then effectively I will then get omega R HIR effective will be equal to H1, and the omega R, which is the rotational the precessional frequency, will be minus gamma times H1. So now the another effect of the RF, one thing is it excited all of those spins as I indicated to you. It will excite a larger number of spins in one go. Apply the pulse RF for a microsecond, then I am able to excite all the spins because I have so many RF fields created with the different amplitudes. Another effect of the RF is that this magnetization, which is equilibrium magnetization of all the spins together, which is along the z axis, which is represented by m naught in the absence of any other perturbation, will now get tilted into the transverse plane. What was along the z axis will now become along the transverse plane. It will tend to get oriented with respect to H1, because in the rotating frame, if you remember, my effective field was H1 only. Therefore the magnetization will have to reorient itself with respect to H1, and the red arrow therefore now comes down, rotates by this. But it will go in a kind of a spiral mode. It will come out because it has to precess around the H1 field and eventually orient itself with respect to H1. Just as the precession was happening around the z axis earlier, now the precession will happen around this, and slowly the magnetic moments will orient themselves with respect to H1. However, this will take time, because this is dependent on the relaxation times of the individual spins. How long it will take to orient themselves, how long it will take to readjust their populations, that is the determining factor for this kind of orientation. But now we are applying H1 for a small time, for a microsecond time. Microsecond is certainly not enough for these spins to reorient themselves into along the H1 axis. So what will happen? The result will be that in the process, as it is moving, if the magnetization is moving like this, and by the time it has come here, I stop the RF, okay, and therefore it won't go back anymore there. So therefore if I make a rotation like this by 90 degrees, then I will have the magnetization rotated by 90 degrees, and that will depend upon what is my tau value. Okay, the tau value, if it is adjusted in such a way that the magnetization is rotated by 90 degree, then call it as a 90 degree pulse. So the magnetization is rotated from the z axis into the transverse plane along the x or the y axis, depending upon how I apply the RF pulse. Okay, now what is the consequence of this? After I applied the pulse and I removed it, if I apply the RF and then removed it, so what will happen? The magnetization has to go back to equilibrium, it has to go back to the z axis. So how does it do it? So that is indicated here. So you can see the magnetization which was on along the y axis, now it will slowly start moving. As you can see here, it will slowly start moving and recover back along the z axis in the spiral manner. And as it is recovering back in the spiral manner, there are magnetic moments which are oscillating in the transverse plane. And these oscillating magnetic moments in the transverse plane, they will induce a kind of a voltage in a detector what you will have on the transverse plane. That small I which is there, that is a kind of a detector, and that will see induced voltage in the detector. So rotating magnetization will induce a voltage, and that will be my NMR signal. The individual spins which are going with their characteristic frequencies, they will all induce a characteristic voltage in your detector. Therefore what I will collect is the superposition of all these individual inductions from the spins, and that is indicated by summation of all of these time dependent functions what we have there for different colors. I have taken here 2 different colors representing 2 different spins represented by K and L, and I will have the superposition of the signals coming from the K spin and the L spin, and this is called as the free induction decay. This superposition is the crux of the new method of recording NMR spectra, and that is called as Fourier transform NMR. This was the basic discovery which was made by Richard Ernst. Now the superposition is a mathematical entity, and let's say analyze it in a mathematical manner. The superposition is a Fourier transform of your NMR spectrum. The time domain function is a Fourier transform of the frequency domain spectrum, and vice versa. So if I take the time domain function, which I call it as free induction decay, and do a Fourier transformation, I get the frequency domain spectrum. Now we see what we have achieved. What we have achieved is phenomenal, because we applied the RF for 1 or 2 microseconds. And how long this signal lasts, the FID which you are detecting free induction decay, that will last for a few hundred milliseconds. Okay, and therefore in few hundred milliseconds you have collected data about all the frequencies which are present in your spectrum. Earlier this used to take you 16 minutes in the slow passage experiment. This you are now collecting in a few hundred milliseconds. This is the phenomenal change with respect to the way we collect the NMR spectrum. No wonder it was a fantastic revolution, and of course that led to the Nobel Prize to Richard Ernst in 1991. So this was the Fourier transform NMR, and you can see an experimental demonstration of that in this slide. See, the top spectrum in this is the bottom spectrum in this is the conventional spectrum recorded on the molecule, which is indicated on the top over there, and that is a small organic molecule, and that one gave you a spectrum which is indicated at the bottom trace there, and typically in 500 seconds. It took 500 seconds to scan through the entire spectrum, the sweeping the magnetic field. Now in the same time, the Fourier transform NMR gave you the spectrum which is given in the top portion of the slide, and that is a significant increase in the signal to noise ratio. So this was a fantastic revolution. It is recorded in the same amount of time, and therefore you have a great enhancement in the sensitivity of your NMR spectrometer. Okay, so what is the consequence of that? The consequence was that you can actually record a carbon-13 NMR spectrum at natural abundance. So here is an example. You see there are 2 cases which I have indicated here. The one which is on the left, which is an organic molecule which contains 3 carbon types, okay, indicated as C7, which is on the left, then you have C14, and then you have carbon 2, 3, 5, 6. And these 2, 3, 5, 6, they are all degenerate, they are equivalent because they have the same chemical shift, and likewise 1 and 4 are the carbons which are equivalent, and therefore they absorb energy at the same frequency, and C7 is a separate one, and that absorbs at one particular frequency. Now in the same slide, the top spectrum shows the coupled spectrum. What is the coupling here? The coupling is the carbon-13 is coupled to the protons. Now if carbon, you remember the coupling which I showed you in the case of ethyl alcohol. If it is coupled to a certain number of nuclei, it will be split into more number of signals. Now in the case of 2, 3, 5, 6 carbons, if you see, and they are split into 1:2:3, 1:2:1 a triplet sequence, which means that this carbon is attached to 2 other protons. Therefore it is a CH2 group. This will tell me that it is a CH2 group. All these 4 carbons are CH2 groups. Likewise, you can also identify what sort of splitting is there for 1 and 4, that is seen in the top spectrum. The top spectrum shows you what sort of a splitting is present, and you can identify what sort of a group, the carbon group it is. Similarly, the C1 also appears as a triplet, and then you have the C14 which is appearing as a doublet, and therefore you can identify what sort of groups they are, and they are overlapping in the top spectrum. The signals from 1 and 4 carbon and the C7 carbon, they are overlapping in the top spectrum, therefore it is not possible to resolve them there. And then when you remove the proton coupling by so called decoupling techniques, then you get the bottom spectrum which shows you exclusively the carbon lines in your spectrum. and therefore this becomes an important tool to identify what sort of a molecular structure it is. On the one hand, you know what is the chemical shift of the individual carbons, which gives you the functional groups, their nature, and then it also shows the multiplicity, which will tell you what sort of a carbon it is, whether it is a CH group or CH2 group or CH3 group, it will tell you that. Similarly, the spectrum on the right, you can see there it has 4 different types of carbons. You have 4 different carbons there, and those are all indicated. This is the proton decoupled spectrum, and it is telling you that okay, there are 4 different types of carbons present there. They have slightly different intensities. The intensity difference is primarily because of the relaxation differences of the individual carbons, and that happens because of experimental parameters what you choose, and you will have different kinds of intensities in this particular case.